In this video, we will analyze the main characteristics of a conventional amplitude modulation. And we will use the analytical expressions of the time average of the autocorrelation function and of the power spectral density for this analysis. In particular, if we look at the time average autocorrelation function, we have this expression here, and this expression is going to be useful to analyze the power of the conventional amplitude modulation, because the power of a random process can be obtained if the process is cyclostationary by the value of the time average of the autocorrelation function at 0. Cosine at 0 is equal to 1, and then we have this term over here with the autocorrelation function evaluated at 0. Expanding this result, basically what we have is two terms. The first term is related with the power of the carrier, half of the squared of the carrier amplitude watts. And the second term is related to the power of the double sideband term, the product between the modulating signal with modulation index A and the carrier. The bandwidth of the conventional amplitude modulation is twice the bandwidth of the modulating signal, 2 times W in radians per second or 2 times B in hertz, where W or B is the bandwidth for the modulating signal in radians per second or in hertz. This happens because in the power spectral density of the conventional amplitude modulation we have two deltas, the term corresponding to the spectrum of the carrier, and then two shifted replicas of the power spectral density of the modulating signal, with the scaling factors given by the scaling of MA. MA is equal to the modulation index divided by the range times the modulating signal M of t, and then with a quarter of the square of the carrier amplitude also as a scaling factor. But we have two replicas of the power spectral density of M shifted plus and minus omega c. It is very simple to see that these two replicas are responsible of the bandwidth of the signal, because, for instance, this is an example of the power spectral density of a modulating signal. The bandwidth is W radians per second, and then here we have the two shifted replicas of this power spectral density, shifted to omega c and to minus omega c. And now it's evident that the bandwidth of the modulated signal is twice the bandwidth of the modulating signal. And this happens independently of the shape of the power spectral density of M. Here we have another example with another shape for the power spectral density of M, the same bandwidth, W, and the replica that we have here at omega c has twice the bandwidth that we have in the modulating signal M of t. Finally, we have a summary of the main characteristics of the conventional amplitude modulation. First, we will comment a couple of disadvantages of this modulation with respect to other kind of modulations. First is low power efficiency, because as we saw before, the power has two terms, the power of the carrier and the power of the double sideband term. The carrier itself doesn't transmit information, doesn't contain information, and therefore, in terms of information, is a waste of power. The second drawback is that the spectral efficiency is also low, because to transmit a signal with a given bandwidth, Now we are using twice this bandwidth in the modulated signal. Bandwidth for a conventional PAM is twice the bandwidth of the modulating signal. These are two drawbacks, two disadvantages of the conventional amplitude modulation. The main advantage of this modulation is that by introducing the modulation index and by avoiding the overmodulation, the envelope is proportional to MA, which is proportional to the modulating signal M of t. And therefore, in the envelope, we have the information that we are transmitting. And an envelope detector that can be implemented by means of a diode, a resistor, and a capacity is able to recover the information. At the output of this envelope detector, we only need to remove the mean and to introduce an scaling to recover the original transmitted information signal. This is the main advantage of the conventional AM modulation, and this compensates in some cases the disadvantages of having a low power efficiency and a low spectral efficiency. It's a trade-off between efficiency and simplicity of the demodulator.